Good morning, students. In the last class, we discussed about the interference, that is constructive interference and destructive interference. So, if we continue the topic, so interference we studied in two cases. That is one constructive interference and another one is destructive interference. And in that we have in terms we studied in terms of path difference and also in terms of the phase difference. If we generally summarize the interference, that is constructive and destructive. So considering two sources of two coherent sources S1 and S2, coherent sources S1 and S2. This one has source S1 and this is source S2, and P be any arbitrary point in the medium. Arbitrary point in the medium. So P must be anywhere in the medium. Either we consider here in the middle or somewhere in the medium. Then if we consider somewhere here, so this one is the point P. So in terms of path difference, we will write in terms of path difference, that is S1P minus S2P, that is S1P difference of S2P. So this symbol represents what? The difference. Difference means either S1P minus S2P or S2P minus S1P, that is equals to n lambda. So S1P difference of S2P is equals to n lambda. So where n is the integer, that values ranges from 0, 1, 2 up to n. Right? So if we substitute the value 0 here, then the RHS becomes 0, then S1P is equals to S2P. So if that is in the last class we studied the case one, that is S1P is equals to S2P, then we get the constructive interference and we get the maximum intensity. So if it is 1 lambda, then also we get the constructive interference and the intensity is maximum. So here we get the intensity I is equals to 4 I naught. So this interference we call as constructive interference. This is for the constructive interference. Constructive So if we write the interference by using the path difference, means the difference of S1P to the difference of S1P and to S2P is equals to n lambda, then we get the intensity I is equals to 4 I naught. So this one is the maximum intensity. Then this one we call as constructive interference. So here the two sources are the coherent sources and P is the arbitrary point anywhere in the medium. So this is in terms of path difference, we write the difference of S1P to S2P is equals to m lambda. So next another one case is the difference of S1P to S2P, that is equals to n plus 1 by 2 into lambda. So here the value n is the integer, so ranges from 0. So if we substitute n is equals to 0, then we get half lambda. So here we get the intensity I is equals to 0. That is, we get the intensity I is equals to 0. Then this interference we call as destructive interference. Destructive interference, right? So these are the conditions for the constructive interference and destructive interference. If they ask the condition for the constructive interference, means you have to write S1P, difference of S2P is equals to n lambda. So this is in which case, so this is we are using the path difference. So path difference is the distance between S1P to the distance between S2P. As we studied earlier in the yesterday's class, we studied in detail, that is we considering three cases when the point P is at a same distance from S1 and S2, well, it is not equals to the S1 and S2, right? So constructive interference, the condition is the difference in the path is equals to lambda and its intensity is maximum, that is 4 I naught. And in case of destructive interference, S1P, the difference of S2P is equals to n plus 1 by 2 into lambda, and here the intensity I is 0. So next, if we study in case of phase difference, so this is all about the path difference. So if we study in case of phase difference, right? So here also S1 and S2 are the coherent sources, they are vibrating in phase. Then P is a arbitrary point anywhere in the medium. Then we can write the displacement produced by the source S1. We can write Y1 is equals to A cos omega T, right? So here Y1 is the displacement which is produced by the source S1, right? So y1 is the displacement which is produced by the source S1. We can write y1 is equals to A cos omega t. Next, if we write same for y2, so y2 is the displacement produced by the source S2, then we can write y2 is equals to A cos of omega t plus pi, where pi is the phase difference between these two sources, where pi is called as phase difference, that phase difference between the two sources, that is S1 and S2. So then we get the resultant displacement y is equals to y1 plus y2. So the value of y1 is A cos omega t plus the value of y2 is A cos omega t plus pi. So in these two terms we have the common term, that is the amplitude A is same. Then we know the trigonometric formula cos A plus cos B. So the formula of cos A plus cos B is cos of A plus B by 2 into cos of A minus B by 2. That is 2 cos of A plus B by 2 into cos of A minus B by 2. So if we substitute that formula here, then we get A into 2 cos of, here A means omega t plus B means omega t plus pi divided by 2 into cos of A minus B. So here A is omega t minus of B means omega t plus pi divided by 2. So this is the trigonometric formula, that is cos of A plus cos A plus cos B, that is equals to 2 cos of A plus B divided by 2 into cos of A minus B divided by 2. Then if we simplify here, we get A into 2 times of cos of omega t plus omega t, 2 omega t divided by 2, we get omega t plus pi divided by 2. So here cos omega t minus omega t, so plus omega t minus omega t get cancelled, that is minus into plus minus, cos of minus pi by 2, that is cos of minus theta we can written as cos theta, then we can write cos of pi by 2. So if we rearrange here, the resultant displacement y is equals to 2a cos pi by 2 into cos of omega t plus pi by 2. So if we observe here means, so this represents the wave equation and this whole term gives the amplitude of the resultant wave. So 2a cos of pi by 2. So this one is the amplitude of the resultant wave. This is the amplitude. So if we write the intensity for this equation, so if you write the intensity for the resultant amplitude, so that is I is equals to a square, amplitude square, that is 2a cos pi by 2 whole square. So this can written as I is equals to 4a square cos square pi by 2. So if we write the intensity for the individual wave, that is I naught is equals to, we get I naught is equals to a square. The amplitude of the individual wave is a square. Then here we can write I is equals to 4 I naught cos square pi by 2. So here the intensity varies. So here 4 is the constant, I naught is the constant. So it only depends on the phase difference pi. So if pi is equals to 0, comma 2 pi, that is plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, so on. Then, so if you observe here, when we put the angle pi is equals to, that is phase difference pi is equals to 0, then this whole term become 0, then cos 0 value is 1. So 1 into 4 I naught is 4 I naught, then we get the maximum intensity I is equals to 4 I naught. So if we get the intensity is maximum, that is 4 I naught, then this is the condition for the constructive interference. So as we previously, in case of part difference also we saw that when lambda is equals to 0, S1P is equals to S2P, then we get the intensity is 4 I naught, then that condition we call as constructive interference. So here, if pi value is 0, 2 pi, so if we substitute here 2 pi, then what happens here? 2 pi divided by 2 to get cancelled, that is cos square pi. So cos square pi is, cos pi value is minus 1, that is square is plus 1. So 1 into 4 I naught is 4 I naught. So if we further substitute the values, then we get the intensity 4 I naught. So this condition is for constructive interference. So for constructive interference, the phase difference pi varies. That is, the values of pi is 0 to plus or minus 2 pi, plus or minus 4 pi, and plus or minus 6 pi. Then we get the resultant intensity I is equals to 4 I naught. So if we substitute the value pi, that is equals to plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, that is in the odd terms of pi, then we get the value here. If we substitute pi by 2, that is cos 90, the value of cos 90 is 0, so 0 into 4 I naught is 0, then we get the resultant intensity I is equals to 0. So if intensity I is equals to 0, then the interference we call as destructive interference, right? So that condition is, so this one is the main for the phase difference. So for 5 marks, if they ask give the theory of the interference, then we have to write the in case of phase difference and also in case of the path difference. For 2 marks, they may ask for the write the conditions for the constructive interference. Then we have mentioned two. That is, one is in case of path length, that is the difference between the paths is equals to n lambda. The value n varies from 0, 1, 2, 3 like that. Next, in case of phase difference, we have to write the value pi is equals to 0 plus or minus 2 pi plus or minus 4 pi like that, right? So for 2 marks, they may ask few times they ask the conditions, write the conditions for the constructive interference. So we have to write the two cases. One is in case of path length and another one is in case of phase difference. So where pi is called as the phase difference, right? So this is about general form we written for the constructive interference and destructive interference. So if I is equals to 0, then we call that interference is called as destructive interference. And if intensity is maximum, I is equals to 4 I naught, then that interference we call as constructive interference, right? So all these cases we studied here, if the two sources are coherent, that is the two sources are vibrating in phase. So that for that case we get constructive interference. I is equals to 4 I naught and I is equals to 0, right? So next, if the two sources are vibrating in phase, we have fixed intensity, that is the position of the maximum and minimum intensity will not change. That is, if the phase difference remains constant, that is the phase difference will not change with respect to time. So as time passes, the phase difference will not change. I will write the phase difference as pi. Pi will not change as time changes. Then we get the fixed interference, that is the pi is not changing with respect to time, that is the pi is constant with respect to time. Then we get the interference, that is fixed interference, that is the maximum and minimum positions of the interference will not change with respect to the time, right? So that sources we call as coherent sources, that is they are in phase. So this we are studied here. Here the phase difference will not changes with respect to time. So as time changes, the pi value will not change. If the pi value is not going to change, then here we get the intensity, that is fixed intensities. Intensities will also not changing, right? So this is for the coherent sources. So if the pi value will change, the phase difference will change with respect to time, then what happens? The intensity will also changes, that is intensity is goes on varying, that is here is the minimum and here is the maximum. The intensity also changes, the fringes here we are getting will also changes as the phase difference changes, that is intensity is here fixed intensity or interval. So if pi will change with respect to time, here we are not getting the fixed interference, that is the intensities goes on varying. For that reason we are taken as time. So if pi will not change, that is pi will change with respect to time, then we are going to take time average intensity, because the intensity is also varying. If phase differences goes varying means the intensity values also changes with respect to time. Hence, we are taking here the time average intensity. So that is we return I in square brackets. Brackets here. This brackets represents the time average. So time average of intensity I, that is equals to, we write this equation in bracket, that is 4 I naught cos square pi by 2. So here 4 pi I naught is the constant, so we can write outside 4 I naught cos square pi by 2. So as the value of the cos varies from 0 to 1, then the average value, this one represents the time average, that is the average value of cos value, that is 1 by 2, because the cos value is ranging from 0 to 1, then average is 0 plus 1 divided by 2, then we get 1 by 2. This is for the average value. The average value we can write it as 1 by 2. Then here intensity I is equals to 4 I naught. Then I is equals to 2 I naught. That is intensity adds up at every point. So here I naught is the intensity of the first wave for every wave, individual waves. Then the resultant intensity is adds up. So if you write here y1 is equals to a cos omega t and y2 is equals to a cos of omega t plus pi. So if we write the intensity for y1, then I naught is equals to a square, then y2 is equals to I naught is equals to a square. So here the resultant intensity what we get is I is equals to I naught plus I naught, that is equals to 2 I naught. So at any point we are getting the intensities added up here, that is 2 I naught, right? So here the intensities are varying, that is for 0 and that is here is the intensity minimum and here is the intensity maximum. But in case when phi changes with respect to time, then the intensities are added up. The resultant intensity is equals to sum of the individual intensity. Then at any way we get the same intensity. Hence the source which are using here, that sources are called incoherent sources. So what are incoherent sources means? The phase difference always changes with respect to time. The sources which the phase difference changes, then that sources we call as incoherent sources. So incoherent sources, the intensity is adds up, that is I is equals to 2 I naught. So at any way in the interference we get the same intensity as that of the resultant. So here, so this is about the incoherent source, that is two sources which are vibrating abruptly, that is varying with respect to time, that is the two sources are changing with respect to time, then those two sources we are called as incoherent source. So in case of incoherent source we have intensity I is equals to 2 I naught. So in case of coherent sources we have the intensity I is equals to 4 I naught. Right? So this is about the interference, that is the theory of the interference. In case of the coherent sources, here we are considering the coherent sources. In case of coherent sources we have constructive interference and destructive interference, that is intensity changes, but here in incoherent sources the intensity will remains constant. At anywhere we can find the value of the intensity, then it will be 2 I naught. This is for the incoherent sources. So next, if we study interference by using the light waves, interference by using the light waves. So considering two sources, so this one is the source S1 and here is the source S2, which are illuminated from the small pinhole. That is same source. S1 and S2 are the same sources. Right? Yes and yes. So this one is the ordinary source, or I will take here sodium lamp as the source S. Here also sodium lamp and placing in front of two pinholes. That is the opaque screen is made with the small two holes. Here is the hole 1. We can call this one as S1 and here it is the S2. As the waves which are coming from the source will fall onto the screen, that is here is the pinhole, then this will act as the secondary source. So if we call this one as a source S1 and if here we can call the source S2. So if we consider in here the two sources, that is ordinary source or sodium lamp, the lights which are emitting or the emanating from the source falls onto the screen of opaque screen made with the two pinholes. Then if we place one screen here, so here after the waves which are coming from S1 and S2, right, S1 and S2, here we are not getting any interference pattern. This is because of the intensity adds up, that is I is equals to 2 I naught. So here we are not seeing any pattern on the screen. This is due to I is equals to 2 I naught, because here for the sodium lamp, these are the same sodium lamp. Here the phase difference changes, that is vibrates with respect to time of order 10 to the power of minus 10 seconds. So the sources which are vibrating, the vibrating of the order, that is it changes its phase of order 10 to the power of minus 10 seconds. So due to changes in phase of this time, hence we are not getting any pattern on the screen. That is due to the interference, that is intensities which are coming from S1 and S2 are added up. Hence on the screen anywhere if you find the intensities remain constant, that is the value of 2 I naught. Hence we are not find any interference patterns on the screen, right? So here the sodium lamps, considering two same sodium lamps and same are vibrating abruptly, that is very fast, that is phase difference changes, pi changes with respect to time of the order 10 to the power of minus 10 seconds. So for every second the pi value changes. In this time the phi changes. Hence these two sources, that is sodium lamp sources, acts as incoherent source. Incoherent sources. So that's the reason we are not getting any patterns on the interference patterns on the screen. That is, the intensities which are coming from S1 and S2 are added up. So to log the fringes, that is to log the interference on the screen, Thomas Young conducted one experiment. So next we study Young's experiment. That is Young's experiment we are going to study to overcome this one, to find or to log the interference pattern. The arrangements, experimental arrangements is done by the Thomas Young, that is Young's experiment. That's one is the, so this is the difference between the coherent source and incoherent source. So what happens in coherent source means the phase difference remains constant. That is, the phase difference will not change with respect to time. But in case of incoherent sources, the phase difference changes with respect to time. So next is Young's. So we have one derivation from this topic. So that one is a very important derivation. This asked several times for 5 marks. That is fringe width. Derive the expression for the fringe width. So in the Young's experiment, he considered one. So this one I am writing here. It is in 3D. So here we made one. So that is pinhole on the first opaque screen. So this is one opaque screen, and this one is the second opaque screen. Here he made two pinholes. That is, here is S1 and here it is S2, separated by the small distance S1 and S2. So next, here is the screen, right? So placed from here to here, the distance between the opaque screen and to the screen is D, and here is the one, right? So we have three opaque screen. On the first screen, he made one pinhole. So next, in the second screen, he made two pinholes, calling as S1 and S2, separated by a small distance. That is, separated by very small distance. And here is one more screen, that is opaque screen. Here we get the interference pattern. So the source is kept behind the first screen. That is, he made one pinhole. That is the bright source which is kept behind the first screen. The waves which are the light waves which are emanating from this source fall onto the source S1. Here the source which emanates the waves, that is in phase, when it falls onto the S, here also the waves are in phase only. Here also the waves are in phase. Then the waves which emanating from S will reach to the second screen and it falls onto the two pinholes S1 and S2. So here the source which are coming from the S that are in phase, when it falls onto S1 and S2, that is the spherical waves which fall onto the S1 and S2. Here these S1 and S2 acts as the secondary sources. So this one is the primary, here is the main source. So from here it is the first one and here it is the second one. So here it acts as the secondary source. Here the waves which are emanates from S1 and here S2. So these are interfere and falls onto the screen, right? So here we get the interference pattern. So like this. So if we consider any point in this screen, that is any point in this medium, if we consider the point P is here, then we can find the maximum intensity of that point, and also we can find the minimum intensity of that point. So this experimental arrangement is called as Young's experimental arrangement. So in the last we studied we considered two sodium lamps, that is the two different sources which are coming from two separate pinholes. Then the intensity, after interference, we are not getting any interference pattern on the screen, but here he extended that one, that is the source, the brighter source which falls, the waves which coming from this source falls onto the first screen, then from this screen the it separates, falls onto the S1 and S2, then S1 and S2 acts as the coherent source, because here the two sources are in phase, here also in phase, here also in phase, and here the phase difference remains constant. Hence from these two we get the interference pattern. So if we draw in two dimensions, then so this one is the S1 and here is S2. So that is the second screen, source S1 and S2, that is secondary source S1 and S2, separated by the distance D. So the distance between S1 and S2 is taken as small d, and here is the screen. So this one is the screen. So screen is at a distance from the slits. So this one is the slit. From the slit it is capital D. So this derivation is very important, right? So the distance from secondary source to the screen is taken as capital D, and the distance between the two sources is taken as small d. So in the middle. So here, somewhere here is the point P, right? So from the or center, the point P is at a distance x. So OP is equals to x. So what we written in the experiment, that is in 3 dimensions, we have written in the 2 dimensions. That is, we have sources S1 and S2 separated by a small distance d, and a screen is placed at a distance capital D, and we have considered one arbitrary point on the screen anywhere in that screen, that is at a distance x from the center O. So next here, if we draw the length S1P, that is from the source S1, the waves which meet the point P, that is the resultant wave which getting from these two sources, that is S1 and S2. Then here, from here I can write S2P, right? So from this, next we continue the derivation. So from the middle, its distance is d by 2, and from here to here the distance is d by 2, because here the line is exactly middle to the source S1 and S2. Then between the two sources is d, then the distance becomes half, d by 2 and d by 2. So that is the distance from this point to here. So I will take this one as point M and point N. So the distance from P to n. So this total distance is PO and we are minusing the value MO, then we get P value, that is this value is x minus d by 2. So x minus d by 2. Next, the value for Pn, that is the source S2, if we taken here for measuring this length, then from P to N, so this value becomes x plus b by 2. If we considering at P is the maximum intensity from the point O. So here we are considering we getting the maximum intensity P from O, then we can write S2P minus S1P, that is equals to n lambda, that is n value varies from 0, 1, 2, that is writing here difference. The difference of S2P, that to S1P, that is equals to n lambda. So this gives the, in the previous we studied for the maximum intensity we have the path difference S2P to S1P, that is equals to n lambda, then we get the intensity is maximum. So consider here P, we get the maximum intensity, then from the distance O to P, by using the Pythagoras theorem, that is from the triangle P, S1 and M, from the triangle P, S1, M, we can write, so here S1P becomes hypotenuse, right? So from the Pythagoras theorem, this becomes the right angle triangle, then S1P whole square, that is equals to, from S1 to M, so this distance becomes d square plus, so this distance PM distance becomes x minus d, that is x minus d by 2 whole square, that is S1P square from the first triangle, that is from S1P M. So similarly, if we write for the second triangle P S2 M, then we can write S2P square, that is equals to, the length is the distance from screen, that is d square, plus here Pn, the value we have x plus d by 2 whole square. Now, so if we subtract this one, S2P minus S1P, so what we get here is, that is S2P square minus S1P square, S2P square minus S1P square, that is equals to, in the RHS the value is d square plus x plus d by 2 whole square. Next is minus, so minus right here S1P whole square, that is equals to d square plus x minus d by 2 whole square. This one we are getting from two triangles. S2P whole square is equals to d square plus x plus d by 2 whole square, right? So here we are differencing S2P square minus S1P square, that is equals to d square plus x plus d by 2 whole square minus of d square plus x plus, so it is minus x minus d by 2 whole square. Then, so if you further simplify, d square plus, this one is a plus b whole square, that is a square plus that is x square plus d by 2 whole square plus 2 into x into d by 2. So next is minus of d square, then we can write this one as minus d square. So plus into minus is minus. So here is a minus b whole square. So a square is x square. Next minus d by 2 whole square. Next here minus 2ab into minus we get plus 2 into x into d by 2. So if you observe here plus d square minus d square cancels, plus x square minus x square plus d by 2 whole square minus d by 2 whole square. So the remaining here we get is 2 in the denominator and the numerator we cancel, means here we get xd plus xd, that is equals to 2xd. So in the LHS we have, if you observe here, means this is in the form of a square minus b square, then we can write it as s2p minus s1p into s2p plus s1p. So we need s2p minus s1p, then we shift this to RHS, then we get s2p minus s1p, that is equals to 2xd divided by s2p plus s1p. So if you observe here s1p and s2p, as we have taken, this one is very small distance, that is the distance between s1 and s2 is very small compared to the distance between the source and to the screen, that is d is very small compared to d, then s1p is equals to d and s2p is equals to d. Hence s1p is equals to s2p, that is equals to d. Hence we write here, we get 2xd divided by s2p plus s1p, we have d plus d, that is 2d. So 2 cancel, then we can write so if you write this one here, then we get s2p minus s1p, that is xd divided by capital D. So we know this value, that is the path length between the two, s2p minus s1p. Here we have written s2p minus s1p, that is equals to n lambda. Then here we can write n lambda, that is equals to xd divided by d. So we need the position, that is at what position we get the maximum intensity, then we have x is equals to n lambda capital D divided by small d. So this is the condition which we are taken at maximum intensity, then x is equals to n plus lambda d divided by d. Here this is for the bright fringe. Right? So bright fringe, the position at anywhere from the center, that is from O, it is x is equals to n lambda d divided by d. That is for the bright fringe, xn is equals to x, that is equals to n lambda d divided by d. Right? This is the condition which we are taken. The P is at maximum intensity. So if the P is minimum intensity, that is for I is equals to 0, then we taken here, this shifts to n becomes n plus 1 by 2, that is for the minimum intensity. So that minimum intensity we call that one as the dark fringe, right? So for the dark fringe, it is nearer to that of the point P. Somewhere here we get the dark fringes means at the position from the center. Then for dark fringe, that is x is equals to, that is xn is equals to n plus 1 by 2 into remaining same lambda d divided by d. So this is for the dark fringe, and here we get the bright fringe. So when the intensity is more, then that one we call as bright fringe. When intensity is less, then that one we call as dark fringe. So in the previous diagram here we observed that, so here the screen is like this. Then here we have the bands, right? So these bands are called as fringes. The bright band and the dark band, which are together called, we call as fringes. Hence it is when it is maximum intensity, that one we call as bright fringe. When it has minimum intensity, that one we call as dark fringe. So the distance between, so if I write into like this, so in the black means it is dark, in between the white here is the, so this is larger, but so this one we call as, so this right is the bright. Next here, here. So in between the white space we call as dark fringe. So in the red color we call that one as bright. So in between the white is called as dark fringe. So this point is the point. This is the O, that is at the center, because at the center the distance S1O and S2O is same. So at the center we always have bright fringe. So at the center we have bright fringe. So red color, which one is called as dark fringe, bright fringe. So in the dark we call as dark fringe. So like this we are getting the interference pattern. So one is bright, another dark, bright, dark, and bright, dark. The length, that is the width of the each fringes is same. That is the length or the thickness of the fringes are same. That is for bright fringes and also for the dark fringes. So when it is dark means the condition is xn is equals to n plus 1 by 2. So xn is the distance, that is the distance from the center, that is from the O, we get the dark fringe. So from here the x value is 5, then from here to here the value is 5 meter. From here to here we get one dark fringe. So this is the x value, that is the position of x for the bright fringe is, so here it is 3. If we consider x value is 3, then from the center at the third 3 meter we get one bright fringe. So this one is the for n, well, n represent for nth value. If it is 2, 3 or 0, what about the position of the dark fringe and also for the bright fringe? So next is the fringe width, the distance between the two consecutive bright fringe or dark fringes, then that one we call as fringe width. So fringe width is the distance between the consecutive, fringe width is the distance between two consecutive bright and bright or dark fringes. So fringe width is the distance between two consecutive bright and dark fringes. So that one we call as the fringe width. So that is the definition of the fringe width. So if we consider this one, so these are the dark bands, in between we have the bright bands, then the distance between two consecutive dark bands. So this one is the dark band and this one is the dark band. So the distance between these two bands, dark bands, we call as fringe width. So that one is denoted by letter beta. Fringe width is denoted by letter beta. So or the distance between two bright fringes. So this one is the bright fringes. So this is the bright fringe and this is the bright fringe. Then this distance we call as fringe width. The consecutive distance between two bright fringes or two dark fringes, then width we call as fringe width, right? So if we consider for the bright fringe, consecutive bright fringe, that is for nth value and another one for n plus 1 value. That difference we get the fringe width. That is beta is equals to x n plus 1 minus xn. So the difference between xn bright fringe to that of the dark fringe, then we get the fringe width beta. So if we write for the bright fringe, if it is n plus 1, then here n becomes n plus 1. So that is n plus 1 lambda d by d minus the xn value is n lambda d by d. So if we simplify here, n into lambda d by d, n lambda d by d plus 1 into lambda d by d minus n lambda d by d. So here plus n lambda d by d minus n lambda d by d get cancelled. So the remaining is, we get the fringe width beta is equals to lambda d by small d, where lambda is the wavelength of the light, d is the distance between the slit and the screen, and small d is the distance between the two sources, that is S1 and S2. So this derivation is important for 5 marks. And we have several problems they asked on this topic, that is fringe width. Beta is equals to lambda d divided by d. So in the next class we will solve few problems related on this topic. Thank you.